Hello AP Stats students, Mr. Hazelhorst here with your first video for Chapter 3. Today we're going to talk about how to examine relationships using scatter plots and correlations. So there's going to be a lot of important information coming your way, so you're going to want to make sure you're ready to take some good notes. If you have any questions, as always, put them in the form at the end, and we'll get ready to rock and roll through Chapter 3 here. So let's get going. So I'm going to start by taking a step back and looking at where we've been. Through Chapter 1 and 2, we dealt with what we refer to as univariate data. And this is just a single variable at a time. We talked about how to graph it, different kinds of graphs we could use, and numerical summaries that go along with that. All right, we don't want to forget that information. We're going to see a similar pattern arise here in Chapter 3 and how we go about analyzing data as well. And where we're going here in Chapter 3 and Chapter 4 is the idea of bivariate data. All right, looking at two variables at the same time. And ultimately what we're interested in is how does a change in one variable relate to change in another. And ultimately what we want to decide is, are these changes predictable? And can we create a mathematical model to actually make prediction to how a variable will respond to changes in another. All right? So let's begin with some important terms here. So as we talk about the relationship between two different variables, we're going to deal with what we refer to as a response variable and what we refer to as an explanatory variable. And these terms are foundational to Chapter 3. It's going to be really important that you understand them, and the more we work with them, the better understanding we're going to have and how to determine which is which. But just think of the roots of the words. Response variable, it's going to respond, all right? The response variable is ultimately measuring the outcome of a study. What are we ultimately interested in? All right, what do we want to predict? All right, that's the response variable. How we're going to predict it is through the use of the explanatory variable. All right, the variable that's going to influence changes in that response variable. It explains. All right, response variable responds, explanatory explains. We want to keep that in mind. Okay. So as we talk about these relationships between variables, there's a couple of things that we need to keep in mind. So as we think about the explanatory and response variable, most studies look at a relationship between two variables, but it's important to remember that these relationships are tendencies and not ironclad rules. I like to use my grandpa as an example here, all right? He was a smoker. He smoked about 3 packs a day when I was younger, and the guy lived to be about 90. Now he's an outlier in a situation, right? We know as a tendency, all right, most smokers die younger than non-smokers. Again, that's a tendency. It's not an ironclad rule. It doesn't hold true for every single case, but most situations, right, that is a predictable relationship that we could analyze. All right, so that's what we're looking at. But again, just remember it's a tendency, not an ironclad rule. So let's look at an example of identifying the explanatory and response variable. So here we have a good old cartoon from your textbook. Dennis the Menace talking to Margaret, right, selling some lemonade on a hot day. He says, "Sorry, ma'am, our prices go up with the temperature." So we can see here we've got two variables that he's describing, prices and temperature. And what we're looking for is what's the relationship between these two, okay? So again, we want to remember explanatory explains, response variable responds. And based on what we know about prices and temperature, all right, which one controls which, right? What explains the other, all right? And what makes sense in this case is that temperature is going to rise first, right? That's our explanatory variable. After the temperature rises, then the prices are going to correspond to that. And a lot of times in the relationship between these two variables, it won't make any sense to flip-flop these around. Okay, think about what that would mean if we put price as explanatory and temperature as response. We would say if Dennis the Menace raises his price, then the temperature will increase as well. It makes absolutely no sense, right? So again, in this case, it is clearly that temperature is explanatory and price is response, right? Now, once we have the variables properly identified, now it's time to begin to start analyzing the actual data. And I want you to think back to Chapter 1. What did we always do first when we looked at a set of data? Hopefully you just said graph it. Well, that's exactly what we're going to do here in Chapter 3 as well. So let's talk about the type of graph that we're going to utilize to examine the explanatory and response variables relationship. So the graph that we're going to utilize here in Chapter 3 to analyze the relationship between an explanatory and response variable is what we refer to as a scatter plot. Now, later next week, I'm going to show you how to create these on your graphing calculator. This isn't going to be something I really expect you to do by hand. They're very simple. It's just a plotting of points. But we want to talk about what we're actually going to look for, all right? When we're interpreting a scatter plot, what do we want to see? And so a scatter plot, as we analyze it, we're going to use the acronym FODS. Now you might remember in Chapter 1 when we analyzed univariate data, we referred to the SOCs, right? Shape, outlier, center, spread. And it's kind of the same pattern here, but we're going to analyze what we refer to as the FODS. So let's start out with form, all right? When we analyze the form of a scatter plot, we're looking for one of these three terms. Is it linear, is it curved, or is it a cluster? So let's use our examples here off to the side. If I were to describe the form of the scatter plot at top, right, I would describe this as a curved set of data, right? It's clear that that data follows a curve. Now in Chapter 3, we're not going to talk about how to analyze curved data. We're going to save that for Chapter 4. Chapter 3 is going to focus on linear. And that's what we see in our second example, right? This data much better follows a line of best fit as opposed to a curve of best fit, okay? So that's the form step of FODS. The O step of FODS is outliers. Are there any points that don't follow the form that we identified up above? And when I look at both of these sets of scatter plots, neither one of them really has a point that really jumps out at us as a possible outlier. Everything here for the most part follows the general form, so probably not any outliers in either one of these sets of data, okay? The D part is direction, right? What's the direction that the data is showing us? And the terms that we're going to use here are negative association and positive association, all right? Now, this is just basically describing the direction of the graph, okay? And a negative association is one variable increases, the other decreases, and that's what we see in the top function, right? As the percent taking the SAT increases, right, as our x variable increases, our y variable, mean SAT score, decreases, right? The smaller values are off on this right side of the graph. Okay, so this we would refer to as a negative association. The second graph is what we refer to as a positive association. Both variables are going up. Number of beers goes up, that's our explanatory variable. Blood alcohol content on the y-axis, that's our response. This would be an example of positive association. Okay? The final thing that we need to identify is what we refer to as strength. All right? How close do the points follow a clear form? And at this point, as we analyze the strength, it is purely our opinion. And the easiest way that you can determine strength is how quickly did you come to the decision in the form step? How quickly did you decide that graph 1 was curved? Well, we came to that pretty quickly, right? So it's probably moderate to strong strength. Same thing with graph number 2, pretty clearly aligned. Probably not going to have a lot of argument about that. We're in the moderate to strong category, all right? Now, strength with our eyes, it's hard to judge that. So we need an actual numerical value. So let's begin to kind of head in the direction of our final concept for the day. So here we have two more examples of scatter plots, and I want you to decide which one do you think has a stronger linear relationship. Would you say that graph A, the relationship between x and y is stronger, or would you say that graph B, the relationship between x and y is stronger? So think about that for a second. Now, when I've taught this in class in the past as opposed to by a video, most students choose graph B. They say graph B is the stronger graph. And I can see where they come up with that. They say all the points are closely centered together. There's not a lot of gaps between them. Point A, all the points in graph A are a lot more spread out. So I think B is stronger. And I can see that reasoning again. But if you really analyze these graphs, if you analyze the scale on the x and y axis, what do you notice? Hopefully you notice that these graphs are really the exact same set of data. The only difference between them is the scales that are used on the x and y axis, and that's what changes the look at the graph. So what's important for us to realize is that our eyes are really poor judges on the strength of a relationship between two sets of variables. So we need a better way to determine the strength, and that's where the idea of correlation comes into play. Correlation is just simply a statistic that is going to measure the direction and strength of the linear relationship between two quantitative numerical variables. And the variable that we use to represent correlation is R. All right? So again, R is going to help give us information about direction and strength. Now, this will be a very important concept that we use quite a bit in chapters 3 and 4. So we want to have a pretty good understanding of that. So let's try and give you some information about correlation here. So let's start out with 4 facts about correlation. All right, first off, it doesn't matter what you use the explanatory and response variable. You can switch them around, and if you do that, the correlation value is going to remain the exact same. So the strength stays the same, the direction stays the same, regardless of what we put on the x or y axis. All right. Fact number 2. All right, it doesn't matter what units of measure we use. Right, if we change a unit of measure in the middle of a study, correlation will not change. And you're going to find out here in a couple of days that correlation is calculated using z-scores. And z-scores don't change, right? If I change the unit of measure, all that data still relates to each other the same way. Okay, so that's why correlation is not going to change, all right? Fact number 3 deals with the direction of correlation. So a positive R value indicates a positive association for us, and a negative R value indicates a negative association. So it is okay to come up with a negative number here, just like with z-scores. It doesn't matter one bit. The only difference is whether that data is positive or negatively associated. All right, our 4th and final fact deals with the range of R values. So all of our correlation values are going to fall between a -1 and a +1. Okay? We consider -1 and +1 strong relationships. Okay? So we want to be close to 1 or -1. What we want to avoid is 0. Right? 0 means there is no relationship between our two variables. So correlation would say there's no relationship there, 0. Okay? So again, 1 -1 good, 0 bad, and we're going to fall somewhere in between in most cases. So let's try and give you an idea of, okay, what's if I'm not at 1 and I'm not at -1, what's still okay? Now over the next couple of days we'll talk about how to calculate correlation, but here's what I want you to take from this slide. All right, is just looking at the numerical values. All right, what do we consider the weak category? What do we consider the strong category? And the way that I like to think of correlation is think of it like your grade. Okay, anything that is passing for us, all right, we're going to put towards the strong side. All right, so we look at the bottom scales here. We've got a -0.99. All right, that's nice and strong. That's really strong. You look at how linear that form of that scatter plot is. We got a -0.7. Right, not as strong, but not horrible. Right, and 0.9 again, pretty strong. On the weak side, it's when we get into those failing grades, when we get down to that failing range, and that's what we see here. The first graph's an example of a correlation where R is 0. You can see this is just a cluster of points. There's no, is it going up, is it going down? We have no idea. We can't tell that from that set of data. All right. The middle graph at the top, we got a correlation of a -0.3. We can see it's starting to take on a linear form, right? But it's still pretty spread out. There's a lot of width to that, so not a very strong correlation. Same thing with the 0.5, all right? So again, as we analyze correlation, we want to interpret it kind of like a grade, right? Passing good, failing bad. Lower numbers like a -0.7, it's more in the moderate category, but still better than the weak down below, okay? So a little bit more information here about correlation as we finish up on the day. So a couple of things to just be aware of about correlation, and these are things that kind of pop up in multiple choice questions, so you want to think about that for a couple weeks down the road when our next test will show up. But the first caution is that correlation only works with numerical data, right? We can't say there's a strong correlation between blonde-haired people being whatever, right? Correlation only applies to numbers. So it has nothing to do with characteristics or traits, purely numerical data. Okay. Caution number 2 is that correlation does not work with curved relationships, and this is why we need to graph first. Just like in chapter 1, we said graph it first. Graph it first. We're gonna do the same thing here in chapter 3. We're gonna graph it first in a scatter plot. We're gonna look at that form first and decide, is this a linear relationship? If it is, correlation applies. If it isn't, all right, if it's curved or a cluster, does not matter. You can still calculate it, but it does not apply, okay? Caution number 3 is that correlation is not resistant, all right? Outliers are going to have a big impact on correlation, so we need to keep that in mind, okay? And then 4th and finally, correlation is an important measure, but it's not the only measure that we'll utilize, all right? So it doesn't give us a complete picture of two variable data, We're going to need to look at means, standard deviations, other things as well, but it is a starting point. So we'll use it a lot, but it's not the only thing, okay? So that brings us to the end of our first chapter 3 video. We kind of threw a lot of information at you in this one, so I really hope you took some good notes. Again, as always, if there's any major questions that you have, please comment on those on the forum and give me some direction as we set up our lessons the next couple of days. But again, we're going to spend time showing you how to create a scatter plot on your graphing calculator. We'll talk more about the FODs and how to analyze that. We'll eventually show you how to calculate correlation as well. I'm going to show you a couple of different ways to calculate correlation, and we'll spend a lot of time with that value. So hopefully the more we use it, the more comfortable that you get. But again, please complete the form below, and I'll see you guys soon. Have a great day.
Made with Doodlecast Pro.